Alrighty, so what is the binding energy and the binding energy per nucleon of calcium-44? Okay, so the first thing we actually have to do is we have to look up calcium-44. So I'm going to give you this reference. Let's just find that. Calcium-44 is right here, okay? So its mass, notice that it's element 20. You'll need to know that, right? And that here's 44, and that its mass is this number here, right? I'm going to just type that into my calculator, so I've got it. 955,481. 955,481. All right, there we go. That's awesome. All right. So there's that mass. So notice, and also that it's element 20. I'm just, such a spaz. I'll type that into my calculator too, because the 44 will have when we go back there. So let's look at this thing, right? So this is really calcium. It's 44. It's 20. Its mass is 43.955481. Right? Now, basically, the binding energy is the Q value of this hypothetical reaction, right? That we turn this thing into 20 hydrogens, 20 hydrogens, right? And then there would be 24 neutrons, right? 10 neutrons. Okay. Now this is actually in your data packet. You have to look for it. It's in the front, and they give this to you. So if you can't find it, there it is. I think I put it on this assessment, like I put it up at the top. This guy, hydrogen, you'll have to look up. This will be in that same reference that we just went to. Okay, and then this is the conversion of, if we convert that into energy, this is how many MeV it would be, right? So this is going to be, and then of course this side, by the way, is going to have more mass. That if we did all that work to tear this thing apart into this mass, right, this would have more mass. It has more mass because we did work on it. We gave it potential energy, right? So that's an interesting thought, right? If I lift a mass in my classroom or anywhere, right? If I lift it up, it gains mass, which is kind of a funny thing. Okay, so 21.007825s. That's the hydrogen, right? Plus 24, 1.008665. I'd memorize those just personally, right? Okay, so here we go. I'm going to go this guy minus parentheses 20 times 1.007825 plus 24. I'm doing this all in parentheses, uber parentheses. Okay, times 1.008665. And I'm going left side minus right side. Of course, I'm going to get a negative number. Right, and so the mass just increased by 0.408979. Don't round these things, right? All these figures are significant, right? So this side has this much more mass than this side, right? So therefore, to tear this atom apart, we'd have to do this much mass worth of work, right? To convert that into MeV, 1 U in MeV is that, right? So I'm kind of sensitive to that, right? So this is MeV to U ratio, right? Mass and energy. So I'm going to multiply by 931.5, and indeed I get 380.96. Right? And so 381 point, yes, because we have 4 sig figs, we would actually round that to 381.0 MeV, right? With 4 sig figs, right? And then how many per nucleon? Well, nucleons, how many nucleons do we have? That's how many nucleons, right? There's 44 nucleons, right? Nucleons are protons plus neutrons, right? So it's the mass number. And so 380.96 over 44. This is MeV binding energy, right? This is nucleons. So if I divide that by 44, I get 8.658. And that's MeV per nucleon. This is how, if you want to compare the stability of one atom to another, this is how you do it. Large atoms have higher binding energies just because they have more nucleons. It's the binding energy per nucleon that lets you compare the stability of one atom to another. Okay. fact, there's a whole genre of like Q value problems where we give you the MeV per nucleon. We didn't really go there because that's kind of a weird thing, but I have seen those on tests. So anyway, good enough.